Welcome back to another video with us here at LMD and STEM Academy. In this video, we will be working through the June 2018 Unit 2, Paper 2. And so we'll be starting with question 1, and we're at question 1A, which says that the figure below shows the sequence of an organic compound A producing compounds B and C. So let's just take some time to study this sequence. So we look here, we see compound A, and we see that when we add HBr to compound A, we get B. And when we add NaOH coupled with some ethanol, we see that we get C. And so the first thing I would do here before we go any further is I would just try to determine what actually is compound A, like what homologous series does it belong to, and what does it, what is actual structure. And so let's do that before we go any further so that we are clear as to where we're going, okay? So there are two ways that you can, kind of like decouple what's going on here. You can count how many carbons and how many hydrogens there are, so you know what the molecular formula is, and then kind of draw it based off of that. And so when we count up these, we see that we have 6 carbons and we have 12 hydrogens. So we know that from a molecular formula standpoint, it is C6H12, right? And that's a CnH2n situation. And so we know that the compound A belongs to the family of alkenes, right? And so whenever we're drawing out the structure of it, we know we have to have a double bond somewhere in there, okay? And here's a quick little trick. Here's a hydrogen here. Whenever you see a hydrogen separating 2 carbons, you know that between these 2 carbons is where your double bond has to be, okay? So let's just draw that. And so we would draw now C double bond C. So I just drew these 2 carbons. This one is going to have an H on it. So I'm just going to put an H up here. Okay. And then this one also has a methyl on it. So I'm going to put the methyl here. Okay. And then let's look at this other one now. This one has a methyl on it as well. And then it also has an ethyl on it. So see, this is a substituent. We just took care of that. And this is also a substituent, which is CH2CH3. So I'm going to just drop that one right here. CH2CH3. Okay. And so now I know everything I need to know about compound A in terms of its structure. I know it's an alkene. And so now we can move forward. So let's do that. Let's see what else is being asked of us. So moving right along, we're being asked to identify the reaction mechanism leading to compound B. So how are we going to get from here to here from a mechanism standpoint? And then finally, how are we going to get from B to C from a mechanism standpoint? Okay, so that's what we have to do here. So let's try to figure that one out. So compound B, if I'm going to get compound B from compound A, as we said earlier, it's an alkene. So there's a double bond there across which I can add this electrophile. So let's just write that's an electrophile, right? HBr is an electrophile. Remember, it has the H portion and the Br portion. It's a polar bond that's partially negative and that's partially positive. So this portion can act as an electrophile and then can be added across the carbon-carbon double bond. So that would be what? Electrophilic addition to get from A to B. Okay, so we're going to just put that there. All right. We're going to do electrophilic addition to get from A to B. All right. So then now, if we want to go from B now to C, what I would have had here in the middle, when I added the HBr across, I'm going to add the HBr across, and I'm going to apply Markovnikov's rule since this is, what is this? Asymmetric. So I'm going to put the H right there. So I would have HCH3, and I'm going to put the H there because it's going to go where there are already more H's. And then I have my CH3 up here. I have my CH2, CH3 here. And then the bromine would want to go where there are already other more substituents. So that's what I'm working with. And so now, if I have to go to C, what I'm going to have to do, right? When I see this is a nucleophile, that NaOH will act as a strong nucleophile, a supplier of that OH minus. That's what that NaOH is doing, is supplying OH minus. And so that's a nucleophile that's going to have to come in here, right? And kick out this bromine. And so when that nucleophile comes in here, kick out the bromine, we're going to get C. And that is known as, that mechanism that we just described is when a nucleophile substitutes, we call that a nucleophilic substitution. Okay? And if we wanted to get fancy, all right, this is in your syllabus, so it's not like we'll be getting fancy, but like, because this, if you look at this, what is this? This is a halogenoalkane, and it's a tertiary one because the carbon that the halogen is on has 1, 2, 3 other carbons bonded to it. So this is a tertiary halogenoalkane. So let me just write that. It's a tertiary halogenoalkane. So if it's a tertiary halogenoalkane undergoing a nucleophilic substitution, it's a special kind and it's known as a SN1. And it's a stepwise process. So let's just make sure that you're clear on that distinction there. Okay? When it's a tertiary halogenoalkane, we're going to have a special kind of nucleophilic substitution known as SN1. It's a stepwise process. If this were a primary halogenoalkane, you would have SN2, which is a concerted process. So make sure that you know the difference between these two things, okay? SN1 and SN2, as it relates to nucleophilic substitution of halogenoalkanes, okay? And so we could have added that there as well, okay? All right, so now we're ready to move on. So let's move forward. Let's clear everything and move forward. All right, so now we're being asked to draw the displayed formula for each of the following compounds, B and C, and I kind of just did that, right? We just had those there, but let's go ahead and just draw them out again. So we said that we would be adding across the double bond, we'll be adding HBr. And so remember what our alkene structure was, right? And so I had a H up here, I had a CH3 down here, and then I had the ethyl portion, and then I had the methyl portion. And then we said the bromine would go in here where there are already more substituents. So the Br would go here. And then the hydrogen would actually go here because it wants to be where there's already another hydrogen. Okay? So that's based on Markovnikov's rule. So this is my structure here that I would draw. And I just make sure that my carbon does have 4 bonds coming from it. 1, 2, 3, 4. 1, 2, 3, 4. So that's completely saturated, and that's our halogenoalkane, and that's B, right? That's B. Now C, I'm gonna bring C over here where there's a little bit more space. So C, we said we would have nucleophilic substitution, whereby we're gonna kick out this bromine, right, and add in the OH minus, that nucleophile from here. And so that's literally what we need to show. So I'm gonna put C, bam, CH3 from up there. Put my ethyl here. The Br, wherever the Br was, this guy is gonna go and it's gonna be replaced by the OH. So I put my OH right here, and then everything else remains the same. Okay, so everything else remains the same now. So that's an alcohol now that I formed. And you can see that it has what? The carbon that the OH is on is bonded to 1, 2, 3 other carbons. So that's actually a tertiary alcohol. And that makes sense, right? Because we came from a tertiary halogenoalkane. So we would get a tertiary alcohol, okay? So just keep all of these key points in mind as we go forward, okay? So that's what would have been expected of us here. All right, so let's keep moving forward. All right. So now we're being asked to use curved arrows to show the movement of electrons. And then we're gonna write the mechanism for the conversion of compound A to compound B. All right, so remember what compound A was. So let's just sketch it there. Compound A was our alkene, right? That's where we started. That's where the whole thing started, was with this alkene, which is compound A. All right, so let's just get that up there so we see, we have a sense of where we're going, right? So that's what we have, compound A. And then what was compound B? Compound B was our tertiary halogenoalkane. So that's where I'm trying to go now. CH2, CH3. And then we had the Br that was added here to be with its fellow substituents. And then we had the H down here. And then we had the methyl that we had from before in the alkene. And then we had the H up top. Okay, so that's where we're trying to go. So we're trying to go here and we're adding HBr in order to get there. Okay, and so this mechanism, as we said earlier, would be electrophilic addition. So let's just jot that down here, what we need to show. So we're showing the mechanism of electrophilic addition, right? And specifically, because as I said, if we try to split this double bond, like right down the middle, we don't have the sides being equal, right? So that's what we call a asymmetric alkene, right? It's an asymmetric alkene. And if it's an asymmetric alkene, we're gonna have to apply Markovnikov's rule, okay? So these are all things that we need to know before we start to even push arrows, right? That we're gonna need to apply Markovnikov's rule. All right, so let's come down here now. Let's start out. Let's start out now. So step one is that we're gonna have the creation of the carbocation. Okay. So this is step one. We're gonna have our alkene, our asymmetric alkene. So here it is, our asymmetric alkene. I'm just redrawing it here. CH2, CH3. All right. So then we're gonna have our HBr in the vicinity. And let me just color code my HBr again. I'm gonna put the H in pink. And then I'm gonna put the Br in, let's see here. Let's put the Br in orange, okay? All right. And we know that we have a shared pair of electrons between them. This is covalently bonded. Okay? So remember now, my alkene, this region here in the middle, right? Right here, this double bond is a region of high electron density. So it's very negatively charged. And so what's going to happen now is going to see that my HBr is polar, has a partial positive charge here and a partial negative charge here due to the difference in electronegativities of these two atoms. So this, right, my double bond is rich in electrons. It's going to see this positive hydrogen and be like, come, let me extend a bond to you. Let me give you one of my pairs of electrons, and I'll have you come and join our molecule. And then what's going to happen is that the hydrogen will have to just go along and be with this molecule here. And so the bromine is going to then take the two electrons that were in that bond onto itself. And then in the end, what is that going to become? That's going to become a bromide ion that's going to leave, okay? So we're going to get that bromide ion here. So remember now, the electron movement is going to be shown coming from this high region of high electron density to the hydrogen. And then these two electrons are going to move down onto the bromine. And so we get a bromide ion. Okay, so let's just show the intermediate structure then, which is our carbocation. And that's what we're showing in step one, is the creation of the carbocation. So I'm going to just show my arrow then going here, where I have now gotten rid of that double bond. Now it's a single bond. And then the H is still there from before. And then the methyl is still there from before. But now we've added in that hydrogen from the HBr. And it's going to go right here. How did I know it was going to be added right here? It's because there's already a hydrogen there, and hydrogen wants to go and be where the other hydrogens are. And if we look over here, we don't see any hydrogen. So the hydrogen is not going to go there. Okay, that's what Markovnikov's rule says in a nutshell. And so, okay, so now this carbon, let's just write what was there from before. We're going to put back our methyl that was up top, and we're going to put back our ethyl that was there from before as well. And so this carbon, now you realize that it only has 3 bonds because, right, that one of that double bond went down to extend that to the hydrogen. And so now here is going to be positively charged. And so that's now our carbocation intermediate that we made in that first step. So that's our carbocation intermediate. All right. And so once we have that carbocation intermediate, now there's also a bromide ion that's going to be liberated from that first step as well. So we're going to have the Br bromide ion, right? And so now in step 2, what we're going to have is the bromide ion bonding to the carbocation. So that's our second step. And so now we're gonna have this guy coming in. Electrons are gonna be pushed here, right? And so in the end, we're gonna get our final structure, which is now everything remains the same as before. So we have that. We have the C, we have the CH3, we have the ethyl portion that we had from before. And then we're gonna put in our H was there from that intermediate carbocation. And then now we're gonna put in our Br right here. And so you see that the Br went where there are other substituents, again, per Markovnikov's rule. And so this right here is our final product, okay? So I'm gonna write that there, that this is our final product, okay? And so we see that now, as I said earlier, we have a tertiary halogenoalkane, right? We see that the carbon to which the halogen was incorporated has 1, 2, 3 bonds to other carbons. So that's a tertiary halogenoalkane. So I'm gonna write that, that is a tertiary halogenoalkane. Okay? And we're going to move on to part D. Part D says we're supposed to state the name and reagents for a laboratory test that can be used to distinguish between compound C and propan-1-ol. So we have to like know what the structures are if we're going to be, want to think of a test that could potentially distinguish between them. We have to know what we're working with. So, or let's draw back our compound C, right? Our compound C that we made earlier, it was a tertiary alcohol. So it was this one here that we had made. So this was a methyl out here. And we added the H here. And then the Br went away and the OH came in. So that's how we had gotten that tertiary alcohol. So this is what we had from the first part of this question. Right? And so we said the carbon where the OH is has 3 other things, 3 other carbons bonded to it. So we said that that's a tertiary alcohol. Okay? Let's draw propan-1-ol now. Propan-1-ol, let's draw that one. Bam, 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 bam. Let's carry that one out here. So 1, 2, 3, and the propan-1 also under my OH is on my first carbon. And then just fill out everything else with hydrogens. Hydrogen, a hydrogen here, one here, one here, and one here. And when we look at this carbon that the OH is bonded to, we see that there's literally only one other carbon bonded to it. And so we know that that's a primary alcohol. Okay? So what we're doing in essence is we're coming up with a test. What test can you use to distinguish between a primary alcohol and a tertiary alcohol, right? So you might remember that tertiary alcohols cannot be oxidized, right? They cannot be oxidized, right? They cannot be oxidized, while the primaries can be oxidized. Okay? Can be oxidized. So that's going to form the basis of our test. We're going to use a powerful oxidizing agent and then think about what would happen, what would expect in each case. If I can oxidize my primary alcohol and I can't oxidize my tertiary alcohol, let's see what would happen, okay? And that would be a point of being able to distinguish between them. So what we're going to do in the way of a test is that we're going to do an oxidation of alcohols test, and we can use KMnO4 or K2Cr2O7. So that's potassium permanganate or potassium dichromate. And so if I add potassium dichromate to my primary alcohol, if it's a primary alcohol that I have there, then I will see a color change from purple to colorless, right? That's what I would see if I have, in fact, a primary alcohol. If I have a tertiary, I'm gonna see no color change because there's no oxidation that's going on in that one. Okay? For the potassium dichromate, if it was a primary, I would go from orange to green. Yeah, that would be my color change. And then, of course, just as we said, there would be no oxidation for the tertiary. And so you would see no color change, okay? So that's how we'll be able to distinguish between our primary alcohol, which is propan-1-ol, and our tertiary alcohol, which is what we form in this question, which is compound C, which looks like that. Okay? All right, so that's the test that we would use there to distinguish between them. So let's clear this, and now we're going to move on to part E of this question. So part E says that the table below shows some reactions of phenols. So we're to complete the table by indicating the expected observations and the structures of the expected products, if any. All right, and so here we have our reagents that we have at our disposal. Here we're going to put our observations and the structure of, if there are any products that we're expecting. So here's a phenol structure, right? No, phenol is acidic, right? Phenols are acidic in nature, so we got to think about that. But even before that, right, we have to think about the fact that when we have a phenol, there are two functionalities that can be reacting, right? We have the OH portion of it that can be reacting, and we also have the ring portion of it that can be reacting, so the benzene ring itself. So there are a whole suite of reactions that phenols can participate in. So just keep that in mind. But then to go back to this acidic nature of it, right? It's gonna be the phenol as a whole is gonna be slightly more reactive than a benzene would be. And so if I add a reagent like Br2 aqueous to it, all right, that's gonna react with the ring portion itself. And what we're gonna see is a rapid decolorization of the bromine water, okay? So that's our first observation, rapid decolorization of Br2 aqueous. And the second thing I'm going to see is I'm going to see a wide precipitate because we're forming 2, 4, 6 tribromophenol. So that's why we're going to see that precipitate, tribromophenol. So we're going to see that white precipitate, and the white precipitate, the 2,4,6 tribromophenol has an antiseptic smell. And so it would smell an antiseptic, okay? All right, so remember now, if we add Br2 aqueous to the phenol, it's going to react with the benzene portion, the ring portion, and we're going to get substitutions at the 2, 4 and the 6 position. So that's what I'm going to draw here for my structure. I'm going to draw 2, 4, 6 tribromophenol. So my bromines are going to get incorporated in the 2, 4, and 6 positions on the ring. So I'm going to have my OH still there because that part didn't react. It was the ring. And so I'm going to have a BR here. I'm going to have a BR here. And I'm going to also have a BR there. Okay? All right, so that's 2, 4, 6 tribromophenol. And then now, when we have the NaOH, which is a strong base, as we know, and we're adding that to the phenol, which we said is slightly acidic, right? That acidity actually comes from the OH portion of it, right? This part of it. And so what's going to happen then is that we're going to have an acid-base reaction between the phenol and which is acidic and the NaOH. And so we know when we have an acid reacting with a base, it's going to form a salt and water. And so that's exactly the structure that I'm going to draw here. Right, I have my phenol. So here's my phenol. It's the OH portion that's reacting now. And so let's just put in our bonds, right? And so my OH now is going to become O minus Na plus. And then as a side product, I'm going to get water as well, because remember, it's an acid-base reaction. So we're going to get the salt and water. And so this salt is actually called sodium phenoxide. Right? That's the salt of that phenol there. So that's sodium phenoxide that we would get in that case. Okay? So this is the structure for here, and then this would be the structure for here. And these are our 3 observations. Okay? And so with that, we've come to the end of this question. Definitely give this video a like, subscribe to the channel, and if you look on your left here, you'll see the next video up. And if you look on the right here, you'll find our Module 1 playlist with tons of interesting content that will be helpful in getting you prepared for your exam. So thanks for watching, and we'll see you in our next video.